So as we all know, this LLMs are basically black box systems. At least we perceive them as black box systems. We should know how a LLM work to actually use it in real world settings, because there are issues with safety, there are issues with all this bias and stuff. So if we don't know how this works, we cannot actually use it as a safe and trustable system. So for any system to be deployed in a real world scale, the control should be at our hand, right? So the field of NLP interpretability is actually quite nascent compared to the whole history of NLP. So NLP dates back to a long ago, since I think you can talk about ELIZA and stuff like that. But this NLP mainly started around 2016. Maybe I shouldn't use the word started, but actually started to gain traction around 2016, when researchers were primarily studying recurrent architectures like LSTMs and how they function. And interestingly enough, in 2017, Transformer was released. So when this field of interpretability was growing, Transformer drops in. And then Transformers, we don't understand how they work, so we just know the architecture. So this coincidence kind of led to a boom in this interpretability community. So much so that in 2018, the first black box NLP workshop was held in an ACL conference. And as it drops, it becomes one of the popular conferences of ACL. And as more and more works started to come in, ACL actually incorporated this new track called interpretability analysis in their conference. So if we broadly classify the interpretability techniques, obviously it's tough to classify interpretability techniques, but mostly we see there are two broad categorizations. One is behavior localization, another is information decoding. So in behavior localization, what we do is we try to localize the behavior of each component, right? So if you remember, in the last lecture, we were talking about this residual stream perspective of transformers, where we saw how we kind of disentangled the role of each of the component and tried to localize how each component is contributing towards the output. In information decoding, our goal is to kind of decode or kind of learn or kind of interpret from the information within the model, say the hidden states or the activations, how these activations or hidden states contributes towards a particular tasks. So in behavior localization, there are two main categories. One in input attribution, which kind of tries to model what is the role of a particular input token towards the generation of a particular output. In model component attribution, as the name suggests, the role is to understand how a particular model component influences the output. And we will see different categories of it, like logic attribution. Probably will not discuss about logic attribution. We will discuss about causal inferences and circuit analysis. We'll also discuss about probing. We'll discuss about decoding in vocabulary space. And if time permits, we'll look into dictionary learning. So before this new era of kind of which this interpretability field kind of boomed, initially people were also using more simpler techniques, I would say, like distributional semantics and representational similarity. Like we all know, when this word-to-vec dropped, there is this notion of vector space analogy, where we say ki the embedding of, say, king is to queen is proportional to man is to, it will give woman. And that was a kind of start of interpretability using vector space analogical reasoning, ki what was happening within the vector space. Then, just like in computer vision, people use saliency maps and stuff like that, which are easy to visualize. In interpretability, a normal choice was attention maps. So people were trying to visualize attention maps to see which tokens are receiving the more attention, which kind of translates to a particular output. Then there was neuroanalysis, so basically which we will talk in a maybe a different test, but actually it's the same concept. Neuroanalysis is basically analyzing how a particular neuron is responsible for the output, and component analysis and probing we will see next. So first let's discuss about probing, because I think this is the most simplest technique one can use to start with interpretability. So what probing does is, suppose you have any model, it's a n-layer transformer model, let us assume. We want to understand what a particular layer learns, what kind of information it contains. So what we do is we train a classifier on top of the hidden state of the layer. Let us name the classifier G, which maps the hidden state of the lth layer to some feature label. Now this feature label is for some linguistic task which we want to understand. For example, suppose we have a BERT model. We want to understand how BERT encodes the syntactic and semantic understanding of a task. So what we will do is, to understand the syntax, part of speech tagging is a good proxy. So part of speech tagging can be chosen as our probe task, and we can train a classifier which will try to predict the part of speech tags from the hidden state of a layer. And similarly, we can design probes for semantic information, like say coreference resolution or tasks like that. So what is essentially a probe classifier doing? If we look into it carefully, what is trying to model is the mutual information between the hidden state and the random variable, which are the properties of Z. So suppose this Z random variable represents the information required to assess the part of speech tag, and H, capital H, is the random variable which denotes the representations of the hidden state. So if there is any mutual information, so if we go back a little bit, so what does mutual information say? Like if we say mutual information between X and Y, two random variables, it will say how much information can we tell about X if we know Y, right? How much Y can give information about X. Similarly, in this case, we are trying to see how much a hidden state can give us information about a separate task Z, which can be any linguistic task like part of speech tagging. So this is the basic motivation of probe tasks. That is, when we train a classifier, we are trying to predict a property of the input text based on the representation H, as I said. So we are trying to see if the property is encoded somewhere within it, right? If we cannot train the classifier, if we cannot train the classifier, there can be two cases. Either there is no information, or there can be a non-linear information. Maybe we need a more sophisticated classifier. Maybe we need a deeper MLP for that. So that is where one of the kind of challenges of probing comes in. So before going to that, as I discussed, the approach of probing is, for every layer you freeze the layer, so you don't fine tune or train the layers. The model is freezed. You only train the classifier to predict a linguistic property. So the question is, should we use simple probes or should we use complex probes? By simple probes, we mean say a 2-layer MLP. By complex probes, say we mean a 15-layer MLP. So suppose I have a task. I use a probe of layer 2, a MLP of layer 2. I train it. I see there is no improvement in the sense the accuracy is very low on the particular task, say part of speech tag. But when I use a complex probe, I see that suddenly the accuracy increases. So what do I say? Do I say the model contains the information, or is it the property of the probe or the which helps in that accuracy? So this is a very challenging thing of probing, and that's why in one of the papers they propose the idea of control tasks. So what control tasks do is, suppose your probe is part of speech tagging. This is your probe task. Now you define a control task which is basically for every token you define a random number. Suppose there are 40 part of speech tags, right? Now you have labels from 0 to 39 and you randomly label the tokens from 0 to 39. So for this example, the cat ran quickly. I suppose randomly label cat as 37, quickly and dog as 15, ran as 10, and something like that. So this information has no structure in it. So ideally, an MLP shouldn't be able to learn this because this is randomized. The only way an MLP can do good at it is through memorization. So this is what I discussed, like how to design the control task. This CV is basically your randomized, any kind of randomized task. And you, for x, I to t, you just label this randomly, right? Now, look at this. This is basically a real world example from part of speech tagging from a paper. Just look at the accuracy. When I use a 2-layer MLP, the control task accuracy is somewhere around 35%. But the part of speech task, which is our probing task, the accuracy is around some 85%. I increase the MLP hidden units gradually and I make it 1000 MLP units. Suddenly, the control task accuracy jumps up to 86%, and this also increases from 85% to around 92%. But look at the difference. This difference, we call it selectivity. So possibly what is happening here is the MLP is memorizing the labels. So ideally, the probe classifier should be such that its accuracy on the control task is low and its accuracy on the probe task is high. That is, your selectivity is high. So this is one of the way to control that challenge. So this was before all, like 2020, 21, before 2020, this was where people was doing. And suddenly in 2020, this term drops in, which we call mechanistic interpretability, which is kind of going very famous these days. People are working on it. A lot of people are working on it, primarily because it doesn't require a lot of computational resources to start with. So academicians, a lot of academicians are working on it. I myself am working on it. So I'm myself a criminal of this. But so the question is it a new paradigm, or are we just pouring the old wine in a new bottle? Are we just naming it a new thing? So there's an interesting paper in this year's EMLLP. This is a position paper. The paper's name is mechanistic. So what is mechanistic? We don't really know what is mechanistic. No one defines what is mechanistic. But interestingly, the authors actually classify the works which call themselves mechanistic interpretability works can be primarily categorized into 4 categories. One is the narrow technical definition. By mechanistic interpretability, as a very narrow term, what people mean is causal mechanisms. That is, they try to interpret what caused a particular output, what model component actually caused a particular output. What is the causal mechanism of the model? That is the most narrow definition. In a more broader field, any research that uses the internals of the models, uses the activations and the weights and try to interpret from it, people call it mechanistic. From a cultural point of view, on the other hand, there is this bunch of people who call themselves that we are the MI community, and then the papers coming out from them are mostly in the mechanistic interpretability line of works. Interestingly enough, a lot of criticisms has been there of this MI community. Many people argue that people who are working in MI community, they don't really cite the previous CL stuff, computational linguistic stuff, which were there already, maybe in a different name, just like probing. It was there from around 2016, but it is kind of reinvented in the mechanistic interpretability era. And the most broader cultural definitions is you do any interpretability in AI, you call that mechanistic interpretability, the paper sells. So yeah. So but what is mechanistic interpretability then? How do you know interpretability is mechanistic interpretability or not? How do you tell it? So the interesting words which comes here is the reverse engineer. The first paper which talks about mechanistic interpretability in the context of transformer language models is from Anthropic. And that is the paper we were discussing in the previous class, kind of this mathematical framework of transformer circuits, where they call this residual stream perspective and stuff like that. So there they define the field of mechanistic interpretability as attempting to reverse engineer the computations of a transformer. The mechanistic interpretability community has grown, and now ICML 2024 had a great mechanistic interpretability workshop, and they use the similar terminologies. They basically, we are trying to reverse engineer the algorithms implemented by neural networks into human understandable mechanisms. So maybe this is the definition we can go with. So how does this term mechanistic interpretability emerged? So let us go a step back and look into general science. So when we talk about general science, when we talk about complex systems, how do you understand, how do scientists understand how a complex system works? How do we understand how a material performs, whether a material is electrical, how is the electrical conductivity of the material? How do we analyze it? We go into the atoms, study the atoms, look at its enthalpy, entropy and stuff like that, and from that we predict what is the electrical property, what is the magnetic conductivity and stuff like that. Similarly, so basically this is zooming in. We are going into the model, looking at the atoms, looking at the electrons, what is the enthalpy, stuff like that, and predicting is its different materialistic properties. Similarly, neural networks at the end of the day are complex systems. So let us take a leaf out of the book of science and look into the atoms of neural networks. So what a neural network consists of? What are the atoms of neural networks? They are neurons. So this is the key idea behind mechanistic interpretability. We look at the atoms of the neural networks, we look at the neurons, and kind of try to reverse engineer how that output may have happened. This is not a concept which was first used in NLP. This again is something we borrow from vision, right? So they have taken transformer from us, we take something from them. So Chris Olah, when he was at OpenAI, he actually coined this term mechanistic interpretability, and when he started looking into CNNs, networks like ResNet, to understand what kind of neurons actually contribute towards a certain pattern matching or stuff like that. And the same paper, the paper's name is Zoom In, an Introduction to Circuits. This term circuit was introduced, which we already introduced in the last class. So circuit is basically a computational subgraph of a neural network. What is a computational subgraph? So basically the neurons acts at the nodes, and the weights which transfers the activations or the output of one neuron to the other, they act at the edges. So we can represent any neural network as a computation graph, and circuits are basically a subgraph of this which contributes towards a particular task. The hypothesis is that for a particular task, not all neurons are required. Only a part of the neurons in the network actually contributes towards for a particular task. We will see how. Look at this example. This is called a car detecting neuron, right? So the role of this neuron is to detect whether the image is a car or not. So they kind of found that this neuron helps in detecting the car. But there's a catch in here. When you give the windows of the car, the upper part of the neuron excites. This is basically a collection. This is kind of a, you can consider it as a map, like a filter in convolution, right? When you give the car body, almost the whole neuron excites, but the bottom part of the neuron or the map or the filter excites the most. When you give the wheels, the upper part is inhibited and the bottom is excited. What does this tell us? This tells us that a particular neuron is not encoding only single property, rather it is encoding multiple properties of the input. For example, here it is looking at the windows, car body, and the wheels. All three are handled by single neuron, right? So when we try to interpret why the output is, say, a car, it detects it is a car, say. So why it does that? We cannot segregate that this neuron is responsible for the wheel part, this neuron is responsible for the car body. We cannot segregate that. And that is a major problem. That's why these neurons are called polysemantic neurons. And this is a big challenge when we do this kind of interpretability, that a single neuron captures multiple properties. So we cannot distinguish them. As humans, we cannot understand how this happens. So there are three claims in this paper they made. First is features. So features acts as the fundamental units of neural networks. Just like cells in a human body, features are the fundamental units in a neural network. Circuits are basically features connected by weights. And universality claims that analogous features and circuits form across models and tasks. This is a very ambitious claim, I would say, because a lot of criticism of mechanistic interpretive research has been the lack of generalizability across models and tasks. So that is still a challenge. So now moving from computer vision to NLP. So first let us understand what is an IOI task. IOI stands for indirect object identification. So suppose I give you a sentence, John and Mary went to the market. John gave the pen to. So here you have to, the model has to predict, the task is to predict what should come here. So basically from the sentence we can understand that Mary should come in this place. So Mary is basically called an indirect object. And a task of the model is to predict this indirect object or to identify the indirect object. So this paper, Interpretability in the Wild, they first tried to find circuits in GPT-2 for these IOI tasks. So as you can see, there's a similar sentence. When Mary and John went to the store, John gave a drink to, and you have to predict the next word. And this orange, whatever color you are seeing, these components actually look into a circuit, but we will see how circuits work and stuff like that. We'll go into that. So how will you find circuits? So basically there are three steps. We'll go on them one by one. First is you have to isolate a particular task. You have to observe a behavior and create a data set that reproduces the behavior in question and define a metric. How do you measure the performance of the task? Let's look at an example. For example, in this IOI task, the metric can be the logic difference between John and Mary, the two objects in the input prompt, right? So whether it is predicting John or Mary, the logic difference can act as a performance of the model. And there are different kind of tasks like docstring, which tries to predict what is the next parameter from the input function. There is this tracer tasks, which are basically a kind of compiler, and there's the induction task, which the task is to basically predict the next token, where the token already arrives before in the similar context. So these are some of the typical tasks which are used for circuit identification in mechanistic interpretability. The second step is to define the scope of the interpretation. Like I said, we will construct computation graphs. So what will be the nodes of those computation graphs? Are those be attention heads? Are those MLPs, or they are more complex in the sense, are they the residual stream state after certain layers? So what is the granularity in which you are going to break down the model? So that is your scope of interpretation. Obviously you will represent the model as a computational directed acyclic graph, and as I said, what is the abstraction level? In fact, you can go into more granular level. Choose query, key and value activations as separate nodes and work with that. The step 3 is the most, I would say, interesting or most critical for finding circuits. So if I go a little back, so the step 3 is you have to perform a series of extensive patching experiments. We will see what is patching is, and try to prune the unnecessary or the not useful components in the computational graph. So we end up with the subgraph, which actually is important for the task in hand. So we call this activation patching. What activation patching does is, for every node in the graph, for the activation of every node in the graph, it overwrites the activation value using a corrupted activation and runs a forward pass through the model and compare the output values for the clean run and the corrupted run. We will see how. So suppose we have a statement John and Mary. We make it corrupt by changing a single token John with Bob, right? And we see how the output logics differ. For a more real world example, consider that the clean run is the Eiffel Tower is in, right? So the output should be Paris. And the corrupt run is, we just replace the Eiffel Tower with Colosseum. Now, we do 2 forward passes initially. One with the clean run, that is the Eiffel Tower is in, with this input set of input tokens. We do a forward pass. We get a logit for, say, the clean run output is R and the corrupt run output is R dash. So we get a logit for R and a logit for R dash with the clean run, right? Similarly, we do with the corrupt run and get the logics. And now we patch each of the components. For example, suppose we want to see whether the attention head, whether the, say, 5th attention head of the first layer. So we denote it as A1.5. So it is the attention of the first layer, 5th head. Whether it is a part of the circuit which is responsible for the task or not. What we do is, we have this corrupt run, right? We replace the A15 of corrupt with A15 of clean and see how much the change in the logits happen. So basically, if we replace the corrupted input patching with the clean input patching, the idea is the logits of R dash or R prime should decrease and that of R should increase gradually if it is important. If not, they will remain the same. So how will we measure this? So basically what we want to measure is the logit difference between R and R dash in each case. In this case, the logit of Paris and the logit of Rome, right? Let us take an example. Suppose this is my Paris output and this is my Rome output, right? So the activation here is, say, A dash. This is our component of interest for now. Forget, just imagine we are working with a single component and we are here, the activation is A, right? We have already cached this. Now for a patch run, what we do is, this for the corrupt run remains the same in the patched run. What we do is, only in place of A, we replace it with A bar, we replace it with A. Okay. So suppose this input is xi up to here and here it is x1 prime. So this is x1 prime, everything comes the same, only we change the activation at a particular component and we check how much the logit difference varies. If this logit difference is greater than a threshold, we will say that this component is important. If it is close to 0, we'll prune this from the graph and say this is not important for the task at hand. So based on this idea, this ACDC algorithm was proposed, which is basically an automatic circuit discovery algorithm. So what it does is, suppose you have a computational graph G. It first sorts the graph in reverse topological order. So we start from the output and move towards the input. That's how we prune it. And then for every component, we remove the candidate edge, and see here they are using KL divergence. So this is basically a choice. You can either use KL divergence or you can use logic difference. It's up to you based on the task at hand. So they are using the KL divergence between the probability distributions when we use G and when we remove one edge from G, which is H nu. H nu is basically when you remove one edge from G, check the distribution, you keep it, check the distribution. This removal is basically patching, right? And when you do this iteratively, at the end of the algorithm, you are left with a subgraph. As you can see, this is a very computationally expensive algorithm. If we go for each computational graph, like for every component of the computational graph, one by one, do activation patching. So for activation patching, how many runs do you require? Just imagine, one is the complete forward pass through the clip, one is the complete forward pass using the corrupted, and again for every component you do patching and do a forward pass, do patching. So if there are n components, apart from those two forward passes, for every n component you have to patch and do a forward pass, and it's basically a huge number of forward passes through a model, which is very expensive. What can be an alternative solution to it? So this is basically a representation of what we already talked about in ACD server. As an example of a circuit, maybe I should have. So alternative attribution patching. What attribution patching tries to do is tries to approximate this difference, I will see how, as a linear approximation. Let's see how. Suppose we have a model which models I is the input space, the clean input space, and L is our logit space. And we have a specific activation which goes from I to an activation space A, right? So what we were doing is activation patching was for a output M. So the output M, right? We have this model, patched model, where we are running with this R is our corrupted input and A is the activation which we will patch, right? So this M, and we were measuring it using a metric, using any metric P. This P can be logic difference, this P can be KL divergence, that is based on our choice. And we were iteratively replacing this A with the clean activation AC, right? So this PMA I comma A, what is it? Let us understand. This is the our model, this is the clean input, and this is the activation. Let us represent it as a function FA I comma I. So our logit difference, this is basically a logit, this P is logit difference. For now, forget KL divergence. This is a logit difference between the clean output and the corrupted output logits, right? So this function basically represents that logit difference based on your input and the activation you are trying to patch, right? So if for attention head, fifth attention head of the first layer, you're trying to see whether it is important or not. Previously we were doing patching and then doing a forward pass. Now without doing the forward pass, can we approximate that logit difference? Because ultimately what we're doing is we are thresholding on the logit difference and pruning it, right? So this FA, what we were doing, let us go step by step, right? We were first taking the corrupted activation, corrupted input, right? And it had an activation. And we were replacing this activation with the clean activation. That is what we were doing. And we were checking what was this FA. And we were thresholding on it, right? So basically we are interested in the difference between this FA when we have a corrupted activation and a clean activation. Now, Taylor series extension of fx for at a point A, at a point where fx is differentiable, can be written as fa plus f dash a by 1 factorial into x minus a plus f double dash a by 2 factorial into x minus a square plus dot dot. So if this difference x minus a is small enough, if this difference is small, we generally neglect these higher order terms as they go towards 0. Right. Now the assumption is that when you alter just a single activation within the model, just a single attention head, typically for a big model like GPT-2, which is a sufficiently big model, the difference between the activation should not be much. It's not of very high order that will blow up, right? It's very small. So we can approximate it linearly. This is basically a linear approximation. So this fax, ignore the r because the input is the same in both cases. We are patching the activations, remember, the input is the same. So fax can be written as, for at any point A, it can be written as fa plus dou fa by dou a into x minus a, right? Now what activation we are patching? We are patching the activation of the, so what is this A? This A is our activation which we will patch with another activation. So our activation is from the corrupted input R, whatever activation A we are getting. So this A is basically AR. R is, remember, the corrupted input. The colosseum is it, right? So fax can be written as far plus dou fa by dou a x minus ar, or fax minus faar is basically dou fa by dou a at a equal to ar into x minus ar. Now what we are interested in? We are interested in how the logic difference changes when we replace AR with SE, the clean activation. So if we put X is equal to the clean activation, then this term becomes FAAC. So this becomes SE. So FAAC minus FAAR. This is the term we were interested in. We were previously doing using a forward pass. Now, if we assume that these are small numbers, doesn't change a lot for a single token, what it becomes is we have a approximation for this difference we were previously doing using a full forward pass. Now let's see how many forward passes this needs. Obviously you need one forward pass for the clean run and one for the corrupted run. So 2 forward passes you need. After 2 forward passes, you already have this SE minus AR for every component, right? What remains is the derivative of this function with respect to A, the activation. So this can be done by single backpropagation, right? For the activation, the derivative of this function with respect to each activation can be done by single backprop using this FA as the kind of loss function, right? So this attribution patching works with 2 forward pass and 1 single backprop. So instead of n forward passes, it is doable in a single backprop. So it's kind of reduces the computation complexity by a lot. But the challenge is here is this only works, number one, when you change a single token. You cannot change multiple tokens and stuff like that. Second is you are working with a lower granular level. It's like attention heads. If you work with, say, residual streams after a layer, after the whole layer, or after 2 layers, then this approximation that this x minus a will be very less may not hold. So these are some of the things you have to keep in mind, that the main assumption over here is that the activations don't change much when we patch a single token at a certain granularity level. But this scales well, and as I said, it can be done with single clean forward pass, corrupted forward pass, and a corrupted backward pass, and it's scalable. So that is the positives of attribution patching. So now we have covered causal interventions, activation patching, attribution patching, and discussed how do you find circuits automatically, right? Okay. Now, what are some of the uses? How do you use this in the real world? Are there some works which use this and find something? It turns out there are a lot of works, but I chose two of them, two such works which are related to the topics already discussed in the course. One is induction heads. So this induction head is said to be one of the primary source of in-context learning. What induction head does is, what is induction head? Head is basically a circuit. What kind of circuits? It consists of two heads. The first head attends the previous token. What does it mean? Suppose you have a sequence A, B, dot, A, right? So you have to predict the next token. The input is A, B, A. And you have to predict the next token, right? So those of you who are doing project 1, this is something you were looking into, right? The task of the first head is to look at the previous token. So for predicting this token, the previous token is A. So the first head looks where is this A present elsewhere in the context, right? And the second head uses the information to find tokens preceded by the present token. So to predict this token, the first head goes and finds what's the previous token, and the next token, what it does is it copies the next whatever is present, next token is present for the output. It's kind of a bigram searching, you may say. So they found, at least in the 2-layer attention only modules, so a typical way of doing mechanistic interpretability is starting with toy models. You play around with toy models, find some phenomena, and look whether it works for large scale models or not. So what they find is, this is again from the Anthropic team. So what they find is this induction heads implement such a pattern copying behavior, right? For example, this is an input from Harry Potter, and the context were Mr. and Mrs. Dursley of the something, and then again here Dursley was arriving. So it was seen that for when we are dealing with this token Earth, for predicting Lay, the attention heads were looking into the similar previous token Earth. So this red actually says you what is the attention is, where the attention is on, and then other head is looking into Lay, right? So there are a lot of examples. Maybe you can go through the article and see. It's a long article, but this example kind of is one example where it illustrates key, look, this is happening, what we hypothesize, what we see by algorithmic tasks. Basically they prove it using algorithmic tasks and then show, look, for even for this kind of natural language inputs, same thing is happening, right? We also in one of the lectures studied about emerging properties, where after a certain point suddenly in context learning emerges. It so happens that this in context learning score is basically the defined at the loss at the 50th token minus loss at the 500th token. Now you may say, what is it? How does it qualify to be a performance for induction for in context score? So the assumption is that when you are taking on the loss for the prediction of the 500th token, suppose this is a 512 input context length. So 500 token is almost toward the end of the context. So when you are predicting the 500 token, the model has already seen almost the whole context. So if in context learning works, this loss should be low compared to predicting the 50th token. When it is toward the start of the context, it has not seen much. In context learning, of course, cannot happen because it has not seen anything in the context. So if in context learning really happens, this 500 token loss, prediction loss, should be low. When you use a one-layer model, remember a one-layer model cannot have attention head from 2 layers. So induction circuits cannot emerge. we see that this score, this L50 minus L500, is almost parallel to the x-axis, compared to when we do 2-layer and 3-layer and other more layer models. After a certain point, after some 2.5 into 10 to the power 9 training tokens, suddenly this loss drops. And the interesting thing is, at the same time, the emergence of the induction heads comes up in this phase of loss dropping. So though we in other lectures we say that, look, emergence is dependent on this matrix you choose, maybe I am kind of contradicting that, but what we see is, at least in case of in-context learning, the emergence of the induction heads and this sudden decrease in loss happens at the same training time. So how do you measure that these induction heads are emerging? We measure it using something called prefix matching score. So basically we see whether it matches with the prefix or not in simple terms. It's just the attention weight for the prefix and the difference between that, right? The fraction of the attention weight. And the second work is from our lab at IIT Delhi, where we worked on the mechanistic understanding of COT. It was the first work which talked about how do you interpret COT from a mechanistic point of view. So this was recently published in TMLR, and there what we saw was that for a particular task, when we are doing COT, there are 3 subtasks the model is kind of algorithmically doing. The first is the decision key, which this is basically a fiction and ontology dataset. So this dataset doesn't make sense. It's just the entities are randomized kind of a thing. It's like A is B, B is C. Is A is C or not, true or false? That kind of an inductive reasoning based on some fiction and ontologies, right? So for that, what we saw was there are 3 subtasks. Subtask 1, where the model has to make the decision which entity to choose. Subtask 2, where it just copies from the context, similar to induction heads. It copies from the context, suppose it chooses max, and then for the subtask 2 it will search where is max, okay, here is max, then we'll copy is Olympus. And the third is this induction here, not in the sense of induction head, it is kind of induction reasoning, where it has a entity and a kind of suffix to it, something, a reason associated with it. You have to, it has to reason whether given an entity and its role for 2 entities, what can it reason from 2 statements, right? There are 3 subtasks which are being implemented. And to give a brief overview, we see that there are multiple neural pathways that that are deployed to basically compute the answer. And basically there is a functional rift in the model in between, where the first half of the head is first half of the models is more associated with moving the information within the residual stream, and second half of the model is more about coming up with the answers. There are more to it about the which attention is does what. Maybe we should give a read to the paper to understand it. Next, what I said in that classification of interpretability techniques was decoding in the vocabulary space. So what does that mean? So this is another, again, easier technique of doing interpretability. When you have a intermediate residual stream state XL and an unembedding matrix WU, what this logit lens does is it simply projects this hidden state XL into the vocabulary space by multiplying with W. So suppose you multiply W with XL, what it will give is your distribution over the vocabulary when you take softmax, right? So basically what it tells is how or what tokens are kind of pushed at each layer of the model. So you can understand at what hidden state the model is pushing which tokens in the vocabulary, and how this kind of tells you how a particular output is gradually forming within the model as the input as a forward pass happens. Interestingly enough, this is also applied to vision language models, where given the input images, you have to generate some caption or stuff like that, and they use the unembedding metrics at each point to see at each layer how much is each pixel categorized into. So suppose each pixel you have to categorize into couch and table. So when you apply the unembedding matrix, it kind of tells you, okay, this part of the image contains couch and table, this part of the image contains cat, and things like that. You can gradually understand whether when you break, because image is also kind of tokenized when you give into vision language models. So it tells you how each token is treated within the model. And this can further be used for editing vision language models, which we will not go into in this lecture. One more tool in this category of projecting in the vocabulary space is patch scopes, released recently by Google. So patch scopes basically gives you a more generalized framework for probing. So for probing, what we were doing was, we're taking a single model, we are applying a classifier on top of that, say the classifier is F, and trying to predict our output Z, right? So here there is a single model M and a single activation or single layer, whatever you call it. Patch scopes makes it more generalized. More generalized in the sense, it uses two models, model M and model M dash. Now suppose you want to interpret what this particular activation stores, which we were previously seeing the mutual information between X and Z, we were seeing in probing, a similar thing. It applies a function F on it and patches this output of F into the token of the next model, a different model, right? So for example, why I say this is a generalized case of probing. So if I have M equal to M dash, right, this function is, say, identity function, and this layer where you patch it, if it is in the last layer L, then it's basically probing, because when it's the same model here and here, you patch it from layer L to layer L to layer capital L, which capital L is the last layer. Then the last layer, if you patch it, what it will do is, after that, it will just apply the unembedding matrix. So that is what logit_lens does. And similar thing you can do with for a probing classifier. Like here we are not training it differently. So this is kind of a more broader view of probing, in the sense you don't need to train it, but you are looking into what information does that. The objective is the same, to look into what information does that state contain, but you don't need to train a classifier. So from these patch scopes, when M equal to M dash and this layer L in the second model L dash is equal to last layer, it becomes logit_lens. There is interesting use cases of these patch scopes. Like you may ask, when we may use a different model. Suppose we have a model which is not powerful enough, right? So from the first model, suppose we have a input, the largest river of India is Ganges, something like that, right? Now what we do is, we want to test whether a particular activation can extract the entity information within the input. So what we do is, suppose here from the first model, we take the activation corresponding to India, right? For the second model, the input prompt is different. It can be different, it's your choice. For logit_lens, it would be the same. But suppose the input prompt for the second model, suppose this is a more powerful model. The input from the second model is, suppose the largest city of X is, right? So the largest city of X is, this is the input prompt to model M dash over here. And the input prompt to here was the largest river of India is, right? Now what we do is, we take the input activation, not input activation for a particular layer, say AL, from this model, right? And we patch it. Suppose we apply a function F to adjust for the model sizes and stuff like that, and we patch it over in place of X. So X had an activation, we patched it with this AL, and we try to see whether the model can give the right output or not as a answer. Like, we already know the largest city of India is something something, and we want to compare whether that output, say the gold output is C, we want to compare that the output which this gives after patching AL, whether it is same as C or not. If it can, that means this model M in its activation AL was storing entity information of India, it is capturing India. If it is not, then it is not storing entity information. So in this way, this can be an extended thing. One more thing, which is dictionary learning. I will just give a brief overview of it in 5 minutes, and then we'll wrap up. So one thing which I told initially was this polysemanticity, that every neuron has multiple concepts within it which we don't really understand. So these are not interpretable. These are not human interpretable, at least. So there is this thing called linear representation hypothesis. Maybe you can go and read it later, but I will give you the brief intuition behind it. So it says that interpretable features are represented as linear directions in some latent space, whether it can be an embedding space or whatever. And when these features are activated, only when the embeddings you have align with these directions. So suppose you have a basis vector, you have a space, and you have a basis. Within that basis, you have these feature vectors pointing to some linear directions, right? So now you give an input. The features are only activated if your input embedding is aligned with these feature vectors. This is linear representation hypothesis, basically, right? And because there are superposition, individual features may not be informative, because there are a lot of things like Windows. I gave an example of car detecting neuron. It was very hard to disentangle the representations within the space. So there is this concept of privileged basis. What privileged basis basically tells is incentivizes the features to align with the basis dimension. The normal basis which we see in word embeddings or transform residual stream, there is no incentive, there is no explicit incentive for the features to be aligned with the basis. They can be different, like this can be your basis and these are your features, they may not be aligned. But privileged basis explicitly kind of guarantees that the feature will be aligned to the basis vector, and this is what happens in transformer MLPs and also in convoluted neurons. And from there comes these concepts of inductive biases and stuff like that, right? And in the superposition hypothesis, we see key features can't align with the basis. Why? Because the model embeds more features than the dimension of the subspace. So suppose it's a 512 dimensional vector activation, and the number of features which are embedded in it is say 1000. So how can the features align with the basis if it is more than the number of the dimension of the subspace? It can't. So here where sparse autoencoders comes in. It is also called dictionary learning. So what it does is, for every activation X, right, the sparse autoencoders up projects it into an intermediate activation FIX. So this is the encoder, W encoder. So when you multiply X with the encoder matrix, sum it over all i's at the basis, whatever you want, and this gives you FIX. The dimension of this FIX is higher, right? And this DI is basically your decoder. So this FIX, then it passes through a decoder, and this reconstruct X prime. So how do you train these sparse autoencoders? So the idea is this FIX has a higher dimension than X, right? So how do you train that autoencoders? You give the reconstruction loss, and you explicitly give a penalty over the L1 norm of F1, Fi. So basically we are giving a penalty on the magnitude of Fi. so that Fi is less. That is, some components of Fi tends to 0, ensuring it is sparse. Right? This is basically sparse, ensuring sparsity loss, and this is the reconstruction loss, just like we train autoencoder. So clearly, the training of autoencoders is completely unsupervised. So what is done is, just for an example, suppose the activation is 512 dimension. It is the features, the sparse features learned through sparse autoencoders can go, like in the paper we are talking about, towards monosemanticity. There they go up to 1,31,000. So that is approx 256 times of 512. So when you go into such a large subspace, the chances, MLP normally learns this privileged basis. So now the features have a chance to at least align with the basis vectors, right? The idea is, if it aligns with the basis vectors, the features are embedded, we can maybe interpret it. We can disentangle them. So this is what is done in sparse autoencoders. To give an example, they kind of extracted millions of features. This was Claude 3 Sonnet model. For the Claude 3 Sonnet model, they extracted the features which affects each part, different kinds of properties in the output, like bias, like different kind of hateful comments and things like that. And they identified the features where each feature contributes to a particular property of the output. And they showed that obviously this is again very computationally expensive. If you have a lot of power, the computational power, then only you can do it. But they identified this feature which was responsible for gender bias, right? After this, they disentangle them, learn the sparse autoencoders, and do all the stuff. They identify that this feature is responsible for gender bias, and they manually then increase or decrease the specific feature, or maybe remove that, and then they see that these biases in the output are controlled by controlling this feature. So though this is still a very nascent field, it's like 2023 paper, I guess, end of 2023, start of 2024, or if I am not wrong, it is May 2024 paper. So it is very nascent field, is just starting, but SAEs seem to have a lot of promise in them for learning human interpretable features and controlling them for basically AI safety. Right. So with this, I will stop. Thank you.